All right, so in this video, we're going to go over the last two sections in chapter 14, and that is going to be section E, and then later on section F. In section E, we're going to be using two-dimensional grids. Now remember, you can use any form you want. So if you don't prefer a two-dimensional grid, you can use a tree, or you can just go ahead and list everything out if you know how to do that one and that's easier for you. I don't really care which way you do it, but we're going to use this to able to come up with all of the possible outcomes, and then from there we're going to figure out what are the odds of something happening. All right, we're going to go through this kind of quickly and only do one example because the very next section we're going to learn something else, which is going to be a lot easier. But I just want you to see and to apply and to know how to apply what we were just doing in the last section with doing a tree, a list, or a grid, and how that applies to following the probability. All right, so this says two square spinners, each with 1, 2, 3, 4 on their edges are twirled simultaneously. So these spinners, that means that here we have 1, 2, 3, 4. And we have two of these. And we're spinning them. All right, I'm going to write them in two different colors just so that way we can just identify two different colors. All right, and we're spinning them. And we're going to say, draw a two-dimensional grid of the possible outcomes. So for A, we can draw what our Punnett square may look like, but remember, it's not really a Punnett square in this case. We have the options on the red spinner, 1, 2, 3, and 4, and we have the options on the blue spinner, 1, 2, 3, and 4. All right, and then from here, we're seeing what are all the possible outcomes that we can have. So I'm just going to go ahead and finish drawing this table really quick. Sorry for being a little sloppy, but it's trying to get through this video a little bit quickly. All right, and then we're just going to go ahead and list it. So I can get a red one and a blue one. I can get a red one on all these cases, and I can get a red one with a blue 2, with a blue 3, and a blue 4. I can get a red 2 in all of these cases, and I can get a blue 1, a blue 2, 3, and 4. Same thing, I can get a 3 in all of these. Now, you don't have to do the different colors, and they never told us that they're different colors. I'm just doing this so that way you can see the red is going first and just the different spinners. Allowing for you to see that there are different spinners that we're spinning here, because since they would just be the same number for both of them, it might be a little bit harder for you to visualize what's going on. So that's the only reason why I'm using the two different colors. All right, now it's saying draw a two-dimensional grid. That's all we had to do for the first one. So for B, it's saying use this grid. So now we're going to use this to determine the probability of getting a 3 with each spinner. So that means that I'm going to roll a 3, 3. So remember, with our probability, it's what we want over the total. So we're looking for the possibility of getting a 3, 3. Well, there is only one time that we roll a 3, 3. So that means the probability is 1. And how many total rolls do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have a total of 16 events that can happen. So now we would say the probability of rolling, I'm going to put double 3, or spinning a double 3, is equal to 1 divided by 16, which is 0.625, or you can say, 0.0625, or you can say 6.3%, because I will have you round to that third decimal place. All right, now let's go ahead and do the second for the third one. It says the probability of rolling a 3 and a 1. All right, so for letter C, now for a 3 and a 1, this double I. That means here we have two possibilities where the red is a 3 and where the blue is a 3. So both of these are 3 and 1. So now we have a 2 out of 16 chance of rolling a 3 and a 1. So maybe the probability, and I'm just going to say a 3, 1, is equal to 2 divided by 16 is going to give me 0.125 or 12.5%. All right, and now the last one that I'm going to do, an even result with the spinner. All right, and now it says an even result with the spinner. Now, I think this isn't a very good worded question, but what they mean here is that both of the numbers are even. So on your test, I will make sure it's worded a lot clearer where it will say where both spinners will have an even number. So an even result means everything is even, and that happens 4 times. Right? These are the only times that we get an even for both of our cases. So it happens 4 times, and we know that there's a total of 16, so 4 divided by 16. So the probability of, I would just say even, is then equal to 4 over 16, which is 0.25 or 25%. All right, that is it for this section. Let's move on to the next one. All right, now in this last section that we're going to do for chapter 14 and the last section that we're doing before break is going to be section F, and that is compound events. Right? So we're talking about compound events now. So now we're going to dive into this a little bit deeper. And now, rather than having to draw out all of the possible outcomes like we did with that grid in the last section, we will use a shortcut to learn how to solve this a little bit easier. All right, we will now look more closely, at calculating probabilities for combined events. Now, you won't really hear anyone ever say combined events. We will say compound events or compound probability. So consider this event, tossing a coin and rolling a die simultaneously. All right, so we could create a Punnett square like they did here to go over all the possible outcomes where we can have a heads and a 1, a heads and a 2, and so forth. And it says, determine then that it tells us there are a total of 12 possible outcomes. And it says, what is the probability of getting a heads and a 5? Well, if we look here, this is the only way that we can roll a heads and a 5. So the only time it can happen is once out of the 12 total possible outcomes, right? And that will be our answer. But it can be a pain to draw this every time. So let's think about this for a second, all right? And this is the way I will teach you and show you to do it. How many events are taking place? 2. So draw a line for each of those events. So we are flipping a coin and we're rolling a die. We want a 5 and we want a heads. So what are the odds of getting a 5? Well, the odds or the probability of getting a 5 are 1 out of 6. Well, what are the odds of getting a heads? 1 out of 2. After you figure out the odds of getting each of these events, when it's a compound event, and it's something that's going to be important and we'll talk about next, when it's independent, we simply just multiply them together. And it gives us 1 over 12. What you see gives us the exact value when we drew the grid and when we counted it out using all the possible sample spaces. All right, so it will give us the same way, and now we have a shortcut that we can go ahead and just multiply the probability of each event happening. But the key thing is we're going to go through an independent and a dependent event. When it's dependent, it's a little bit different, but it's still the same thought process where we are going to draw these lines. But it's just going to be one thing that we change. All right, so let's move on and go through a few more key terms and then some examples. So one of the things that you need to understand are independent events. And 2 events are independent if the occurrence of each event does not affect the occurrence of the other. So think about what we just did. Getting a head and rolling a 5. Well, whether I get a head on a coin or not, it's impossible for it to affect what I roll on a die. So they're completely independent of each other because flipping a coin and rolling a die have no effect on each other whatsoever. And when or if 2 events are independent, we simply can just multiply the probability of each event happening, and it gives us the total probability of them happening together. So the probability of a 5 and a heads, we learned, was equal to the probability of 5, which was 1 over 6, times the probability of the head, which was 1 over 2, so 1 over 12. And then you would just convert this to a decimal. All right, but the key thing is you need to ask yourselves, are these independent? Does one affect the other? All right, so for this example, a coin and a die are tossed simultaneously. Determine the probability of getting a heads and a 3. Same thing, a coin and a die can never affect each other. They're independent. So the probability of a heads and a 3 is equal to, well, we will create 2 lines because there's 2 events that's happening. We want a heads and we want a 3. Well, what's the odds of flipping a heads? 1 out of 2. What's the odds of getting a 3? 1 out of 6. Multiply them together. That means it is 1 out of 12. Now remember, for your test, I will want you to put this as either a decimal or a percentage. So it's going to be equal to 0.083 or 8.3%. All right, let's move on to the next question. So this question says, Sunil has a probability of 4 over 5 of hitting a target, and Monica has a probability of 5 over 6. If they both fire simultaneously at the target, determine probability that A, they both hit, or B, they both miss. So this one's a little bit trickier in that you might think that they could be dependent of each other, because if they're firing at the same time, that maybe one of them can hit and deflect the other arrow. But in this case, we're treating them as if they're independent of each other, because they're not, whether or not Sunil hits the target is not going to be hitting, because it doesn't tell us that they're firing at the exact same target. I will make sure the question in your test is a little bit clearer than this, but we can imagine that they're firing at their own individual target standing in front of them so they don't affect each other. So now we're trying to find A, the probability that they both hit. So now we look and see our events. Well, here we have Sunil, and here we have Monica. Well, Sunil, we know she hits her target 4 out of 5 times, and Monica hits it 5 out of 6 times. So they are independent. We simply just multiply from each other. Right? We can reduce these first. I know 5 and 5 will reduce to 1 and 1. I know 2 goes into 4 twice, and 2 goes into 6 3 times. So that means it is 2 out of 3. So the probability of them both hitting their target is equal to 2 out of 3, or 0.667, or 66.7%. All right, now for B, the probability that they both miss. Right, I'm going to, give me 1 second. All right, I'm going to just do this one right here. So B, the probability that they both miss. Well, we had to then think about something else real quick. This is telling us of them hitting the target. So I know the probability of Suna hitting her target is 4 out of 5. Well, if she's not hitting her target, we know she's missing. And remember, that means we are finding the complement of it. And to find the complement, we will do 1 minus 4 over 5, or 1 over 5. And I'm going to show you 2 different ways that we can do this. I'm going to show you the long way, and then I'll show you the short way. For Monica, we know hers is 5 over 6. Well, her probability of finding her complement then will be 1 minus 5 over 6, which is then going to be equal to 1 over 6. So then the probability of them both missing, I know it's going to be 1 out of 5 times 1 out of 6. All right, so actually this is the only way that we can do this. There is no quicker way. So then we just multiply. That will give me 1 out of 30. So then the probability that they both miss is 1 out of 30. And then I'll put this into my calculator, and 1 divided by 30 will give me 0.033, or 3.3%. So the probability that they both miss is going to be 3.3%. The probability that they both hit is 66% or 67%. All right. If you have any questions on this, let me know. But that is it for the independent. So now we're going to talk about what happens when they are dependent, where one outcome affects the other. All right. Here we're going to talk about dependent events. So suppose that a hat contains 5 red and 3 blue tickets. One ticket is randomly chosen, the color is noted, and it's thrown away. It's not put back in. And a second ticket is randomly selected. What is the chance that the ticket is red? So now, when we go to do that first event, how many total tickets do we have? We have 8 tickets total. We will have 5 red and we will have 3 blue. When we go to do the second one, the ticket is thrown away. So we now have 7 tickets left. So you see, this event affects the probability of this one. And we would either have 5 red and 2 blue left, or 4 red and 3 blue. So these no longer have the same probability as we started with. It now changes because the ticket was thrown away. So since the ticket was thrown away, it's changing the outcome of the second event. Had they drew that ticket and put it back in, then it's independent, because either way, we would always have 8 tickets and we would always have 5 red and 3 blue. But since they're throwing that ticket away, it now becomes dependent. So the event of the second ticket being red or blue, whatever, because I'm not reading the rest of this question, of the color was dependent or depends on the first color. So 2 events are dependent if they're not independent. Clearly that makes sense. And the occurrence of one of the event does affect the occurrence of the other. A lot of times we will have this, the questions that we talk about, we draw in cards. So if we pick a card, an ace, and we don't put it back in the deck, what's the odds of picking a king next? Picking the tickets, picking a marble, something like this, where we pick something and not put it back. All right, so let's just go over how we can solve this, and I'll show you some examples. All right, so for this one here, for A, it says a box contains 4 red and 2 yellow tickets. 2 tickets are randomly selected, one after the other from the box. The first one's removed. That's the key thing. It's removed before the second ticket is chosen. So that tells me that this is dependent. So find a probability that both are red. So I'm going to draw these 2 lines, because this is how I always think it's easier for kids to understand, because these represent events. And in both, I want to have a red ticket. So what is the probability of getting a red ticket for this first one? Well, first off, we have 4 red tickets, so I know it's going to be 4 out of some number, and there are 2 yellow tickets. So that means we have a total of 6 tickets. So 4 out of 6 odds, I'm picking a red. Well, now, if I pick a red and remove it, instead of having 4 tickets left, I now have 3 because I picked a red ticket. Because since we want to look at both red. I don't care about the probability when we pick a yellow first because that's not the event I'm trying to look at. I'm focusing only when the red happens both times. So I'm only focusing when this red occurs. So that means we now have 3 left here. And now if I picked a ticket and threw it away, I then need to look and say, well, how many total do I have? So this 6 has to also decrease 1 to 5. And once we get the probability of each event, we simply just multiply them together. Well, this 3 reduces this 6 to a 2, and this 2 can go into this 4 2 times. And now we multiply, we get 2 times 1, which is equal to 2, and then 1 times 5, which is equal to 5. So it'll be 2 over 5, or the probability of getting 2 red tickets, so 2 red, is equal to 0.4 or 40%. All right, so we simply just find the probability of each event occurring, and we just multiply them, just like we were just doing. The difference is now we need to think about, okay, what is going to happen to this, what's going to happen to this probability of the red ticket as we move to the second one. All right, now we're looking for the probability where the first ticket is red and the second ticket is yellow. So we're looking for this to be red and then for this one to be yellow. So now the probability of us picking a ticket red is still 4 out of 6 because it's the first one to happen. We're starting this over again. So when we go to pick that first ticket, if it's going to be red, there's a 4 out of 6 chance that it'll be red. Now, so we had 4 tickets. I don't care how many red tickets we have left now because we're talking about the yellow. And here I have 2 yellow tickets. So that means my numerator will be 2. My denominator, we took a red ticket and we threw it away. So now we're down to 5. And once again, we're going to multiply these. So here, this 2 goes into the 6 3 times. Nothing else reduces, so we will just multiply across. 4 times 1 will give me 4. 3 times 5 will give me 15. So then the probability of picking I will say a red, then a yellow, is equal to 4 divided by 15, which is 0.267 or 26.7%. All right, either one is acceptable. All right, there's one more example, then we're done with this video. All right, so a hat contains 20 tickets with the numbers 1 through 20 printed on them. If 3 tickets are drawn from a hat without replacement, that tells me it's dependent. Determine a probability that they are all prime numbers. All right, so before I do this, then let's list out all these tickets. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to pause this and then fill it. All right, these are all of our possible numbers. We are picking 3 tickets. We want them all to be prime. Prime. All right, now let's highlight all of our prime numbers. 2, 3, 5, 7, 11, 13, 17, 19. So how many prime numbers do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So here we have 8 prime numbers. So that means on this first event, we have an 8 out of 20 chance of picking a prime number. We're assuming that we pick a prime number. So after picking this prime number here, that means we'll only have 7 prime numbers left. So then the odds of us picking a prime number next would be 7. And now we picked one number. Let's just say we picked 2. Now we're down to 19 numbers left to pick because we picked one of them. So let's say we picked 3. So now we're down to 6 prime numbers left, and there's 18 total numbers left. And now we will multiply these across. So let's just reduce these fractions first. Well, I know 4 goes into 8 twice, and 4 goes into 25 times. I know 6 goes into 18 3 times. And that looks like everything that I can reduce. So then I will go ahead and multiply across, and this will give me 2 times 7 times 1 is 14. 5 times 19 times 3 is going to be equal to 285. So then the probability, let's just scroll down this a little bit, the probability of 3 prime numbers is equal to 14 divided by 285, which is equal to 0.049 or 4.9%. All right, that is it for this section, everything that you will need to know. And we're done with everything up until we get back from our break.